Hey, hello everybody. This is Mr. Ainsworth here, and we're in Section 5, Chapter 3, and we're going to be talking about limits to infinity and how to use them to find horizontal and oblique asymptotes. And we'll also use the squeeze theorem sometimes to help us out. So let's first define what it means to be a horizontal asymptote first. All right, we say that the line y equals L, where L is some real number here. Okay, it could be negative, positive, or zero. It doesn't really matter. It's a real number. Is a horizontal asymptote okay, of the function f, of f can be anything now, if the following happens. If the limit as x goes to infinity of the function here equals that real number L. Okay, so if you get a real number after you take the limit of the function, you have a horizontal asymptote at L, and it's called y equals L. All right, so remember, it's an equation, y equals L. It's a horizontal line. Now, you have the other case of the limit to going to negative infinity as well. So I'm going to say and the limit as x goes to negative infinity of the function, that may be equal to L2. But L has to be a real number. It has to exist if you have a horizontal asymptote. We call this looking at the end behavior of the function. Okay. Now, in order to evaluate limits to infinity, you need a previous theorem. So let me recall Theorem 310, and it's one that we need here in just a minute. So I say if R is a positive rational number, positive rational number, and C is any real number, okay, then the following limit applies. Then the limit as x goes to infinity, those are going to infinity, just like my definition of a horizontal asymptote here, of c divided by x to the r here is equal to 0. Now why is that? Well, the numerator, notice, is any real number, so it's constant. So c is a constant. And the denominator here, if you take x and take it to infinity, that means the denominator here is getting extremely large. In fact, it's getting infinitely large because r is a positive rational number. So as x increases, x to the r increases. So the denominator here, this x to the r, is getting infinitely large. Okay, now if you take and this, remember, c is just a constant. So if you take a constant divided by an infinitely large number, the size of the fraction gets infinitely small. And if it's getting infinitely small, it's approaching 0. Alright, we need this theorem to evaluate limits to infinity, as you'll see in these three cases as x approaches infinity. On this first limit here, you notice that the degree of the numerator is 1 and the degree of the denominator is 2. So the degree of the numerator here is obviously smaller than the degree of the denominator. Let me see, make sure I say that correctly. The degree of the numerator is smaller than the degree of the denominator here. So in this case, the denominator, since it has a higher degree, is going to increase much faster than the degree than the expression in the numerator. And when the denominator increases faster than the numerator, the size of the fraction is going to get smaller and smaller and smaller, and it's going to go to 0. So we're going to see that this limit actually is 0. The way we handle this kind of limit here is we take the term here, degree, which is x squared, and we divide all terms by it. Okay, so let's try that. So we're going to take the limit as x goes to infinity of 3x divided by x squared, which is 3 divided by x, minus 2 divided by x squared, all divided by 5x squared divided by x squared, which is just 5, plus 4 divided by x squared. Now, according to our theorem above here, that all these fractions, where all the denominators are getting infinitely large, are all going to have a limit of 0. So if you apply the limit, these limits are 0, that limit is 0. Alright, and what you're going to get is 0 minus 0 divided by 5 plus 0. Well, that's looking like 0 divided by 5, which is 0. So this limit here is 0. So if this was an actual function right here, we would say it has a horizontal limit, and its name is y equals 0. It happens to be the x-axis. Okay? Now that's when the degree of the numerator is less than the degree of the denominator. Degree of numerator less than degree of denominator. Okay. Oops. That's case 1. Now case 2, degrees are equal. Degrees are equal. Notice right here, degree 2, degree 2. Okay, now here they're going to increase at the same relative speed. So, what's going to be happening here? Well, we're going to take both of these, all these terms here, we're going to divide everything by x squared and see what happens. So I'm going to take the limit as x approaches infinity here of 3x squared divided by x squared, which is 3, minus 2 divided by x squared, all divided by 5x squared divided by x squared, which is 5, plus 4 divided by x squared. Okay, and notice here that we have this fraction here, the first fraction, that's going to have a limit of 0. The other one down in the denominator is going to have a limit of 0. And so this limit here is going to be 3/5. It's going to be 3 minus 0 divided by 5 plus 0, which is 3/5. So when your teachers last year in Algebra 2 said, look at the lead coefficients of your highest degree terms, okay, right here, 3 and the 5, and divide them to get your horizontal asymptote, they were right. And it was all because of this limit rule here. So if this was an actual function here and we wanted to find its horizontal asymptote, we'd say it's y equals 3/5, a horizontal line. Now the third case is when the degree of the numerator is greater, degree of numerator greater than degree of denominator here. So that means that the numerator is going to increase faster than the denominator, and because of that, the size of the fraction is going to get bigger and bigger and bigger. So I expect this limit to be infinity here. The size of the fraction is getting infinitely large as x gets large. Alright, because of the third degree term in the numerator overweights or increases faster than the 5x squared as x gets large. Okay, so we're going to still do what we always do. We're going to take a look at the highest degree term here, which is x cubed. We're going to divide everything by x cubed. So in this case, the limit as x goes to infinity of 3x squared divided by 3x cubed divided by x cubed is 3 plus, or actually minus, that's a mistake, minus 2 divided by x cubed, all divided by 5x squared divided by x cubed, which is 5 divided by x, plus 4 divided by x cubed. When we evaluate all these limits, we're going to get 0 here, 0 here, 0 here. So you've got to be careful in this one because it looks like 3 minus 0 divided by 0 plus 0. So it looks like 3 divided by 0, which is undefined. However, you've got to remember that these are just limits, and these are values that the function approaches, not what they're equal to, because these fractions can never be equal to 0. They're actually, these zeros represent infinitely small numbers. So this right here is just an infinitely small number, okay? And so what do you get when you take a 3 divided by an infinitely small number? Well, you get an infinitely large number here, and we call that infinity. Okay, so this limit is infinity. So when the degree of the numerator is greater than the denominator, you're going to always get infinity there. So this function, because this is not real, okay, the horizontal asymptote does not exist. Okay, because it has to be equal to L, some real number there. So in this section, what you're going to be doing is taking a look at functions. You're going to be trying to find the horizontal asymptote, and to find it, you take a limit to infinity and to negative infinity, and see if you get a real number. And if you do, you have a horizontal asymptote. So in example 1 here, we want to take a look at the limit as x goes to infinity of the function 2x cubed minus 4x squared minus 1, all divided by 2x minus 4, minus 4x squared plus 7x cubed. Now in this case, you're looking at the highest degree terms here, and that's the 2x cubed and the 7x cubed. so you divide everything by x cubed. And so what you get is the limit as x goes to infinity of 2 minus 4 divided by x minus 1 divided by x cubed, all divided by 2 divided by x squared minus 4 divided by x plus 7. And all the fractions have limits of 0. Okay, so that has a limit of 0, that has a limit of 0, that has a limit of 0, that has a limit of 0. And so what you get is 2/7. Well, we should have expected that because we look at the lead coefficients when the degrees are equal, and it's 2 and 7. We divide the 2 and you get 2/7. So we say that the horizontal asymptote of the function is y equals 2/7. Okay, now number 2, the degree of the numerator is less than the degree of the denominator, so I expect this limit to be 0 and to have a horizontal limit at 0, or y equals 0, excuse me. So again, you take the limit as x approaches infinity of x divided by x squared plus 1. You divide everything by the highest degree term, which is your x squared term, just to prove your point, and you get the limit as x goes to infinity of 1 over x divided by 1 plus 1 over x squared. And remember that this limit here is 0, that limit is 0, and so you get 0 divided by 1 plus 0, which is 0. So we got what we expected. So the horizontal asymptote is y equals 0, it's the x-axis. Okay? On this next one here, on number 3, we have a sine function divided by x, so sine x is divided by x. And when we try to find the horizontal asymptote, what we want to do is take a look at the limit as x approaches infinity of sine x divided by x. Now to evaluate this limit, what we have to do is use the squeeze principle, because the techniques I just used above apply to polynomials only. Okay, so on this one here, what I want to do is bound this function by two functions that I can take a limit of, which have the same limit. So we know that negative 1 is less than or equal to sine x, which is less than or equal to 1. Sine is always bounded between negative 1 and 1. As x approaches infinity here, x is a positive, infinitely large positive number, so it's positive. Okay, it's greater than 0, it's positive. So if I divide everything by x, the order of the inequalities don't change. So I'm going to divide everything through by x and build my function here. I'm going to take the limit now as x approaches infinity. 1 over x there, negative. And I'm going to take the limit of the middle function as x approaches infinity. I'm going to do that for everything. Okay, as x approaches infinity. And notice that this limit 0, that limit 0. So my sine, the limit in the middle, must be also be bounded by these two zeros. It must be squeezed by the two zeros, so it must be 0 too. And I'm talking about this limit in the middle. It must be squeezed by two zeros, so it must be equal to 0 as well. So I'm going to say that the limit as x approaches infinity here of sine x divided by x is also equal to 0. And that tells me that y equals 0 is a horizontal asymptote. That's my end conclusion. Okay? Now functions also have what are called oblique asymptotes too. Oblique, slant means the same thing. Okay, and that happens when the degree, okay, of the numerator is exactly 1 degree higher than the degree of the denominator. It is exactly 1 greater than the degree of the denominator. 1 greater than, exactly 1. Okay, and greater than the degree of the denominator. And you notice in this case down here, on my example 4 here, we have a second degree function divided by a first degree function. So the degree of the numerator is exactly 1 higher than the degree of the denominator. So we have one. This function has an oblique asymptote. All right, it doesn't have a horizontal because the degree is higher in the numerator, but it has an oblique. Okay. So how do you find it? Okay, well, you use long division. Okay, so let's go ahead and perform our last example here. So we're going to take x squared plus 9x, and we're going to divide it by x plus 5. When you do that, you look at your first terms. You take x squared divided by x, and you get x. And x times x plus 5 is x squared plus 5x. And then what you want to do is subtract your result. You get a remainder. X squared minus x squared is 0. 9x minus 5x is 4x. There's your remainder. Then you divide again. So 4x divided by x is 4. It's positive, so I put plus. 4 times x plus 5 is 4x plus 20. And then you subtract. 4x minus 4x is 0, and then you got to subtract the 20, and you get a remainder 20. So minus 20 divided by x plus 5. So this function here is actually equal to x plus 4 minus 20 divided by x plus 5. And that's my function written in a slightly different way. And if I want to analyze my horizontal asymptotes, what I do is I take a limit to infinity here. Okay, and I take the limit of infinity of x plus 4 minus 20 divided by x plus 5. Alright, this fraction here is going to have a limit of 0, but this is going to be infinitely large because an infinitely large number plus 4 is infinity. So I'm going to get infinity here, which is obviously not real. It does not exist. And that tells me there's no horizontal asymptotes. Okay, no horizontal asymptotes. However, it has an oblique one. And my oblique asymptote is the linear function, this portion right here. This gives me the oblique asymptote. We'll call it OA, oblique asymptote. Because what happens is that this function behaves like x plus 4 as x gets really, really large, infinitely large here, because this fraction becomes negligible. Okay, it becomes so infinitely small that subtracting it from x plus 4 doesn't really do anything. So it behaves like a linear function. So my oblique asymptote is y equals x plus 4. It's that line. Now let me show you why. So let me go to a graphing program here and show you what I'm talking about. This is so you can understand it better here. I'm going to take our rational function, which is y equals, x squared. Let me go back here. Quantity. X squared plus 9x. I'm going to divide that by x plus 5. Oops, that's not it. Let's start over here. Quantity. Got to input the right numbers here. X squared. There you go. And then plus 9x plus 9x. Alright, I'm going to divide that now. There we go. X plus 5. And then I'm going to graph that and show you what it looks like. There we go. Here's your function here. Now notice it's let me zoom out a little bit more so you can see it. Okay. Now notice that as x gets large to the right, it flattens out to a line. As x gets large to the left, negatively, it flattens out to a line. Look at that. When I zoom out, you can see it. Okay, now we just found earlier that the oblique asymptote is x plus 4. Y equals x plus 4. So let me plot that too. And so you can see that on the graph as well. So y equals x and then plus 4. And notice that, let me zoom in a little bit here, that the red line, the asymptote here, or the one in purple, our original function here, approaches that red asymptote in red, y equals x plus 4, as x goes to the right, as x gets infinitely large to the right, it approaches that asymptote, and as x gets negatively large to the left here, the function in purple approaches that red line. So it has an oblique asymptote, it has a vertical asymptote because the function is undefined there, but it doesn't have a horizontal one because that limit was infinity and it's not a real number. Okay, so your job in this section is to find oblique and horizontal asymptotes using limits to infinity. To give you a homework shot, give it your best. I'll see you tomorrow.